Hello and welcome to our lesson on solving trig equations, day 4. So in this topic we're going to be using double angle identities to solve. And really no new strategies in this lesson. It's just sort of a culmination of a couple of our other strategies. So the first thing we're going to do is looking at making a substitution, substituting in a double angle. Now we've talked about making substitutions using identities already. We've seen that we use identities to, again, make substitutions with the goal of getting one trig function in the equation. So for example, if we look at number 1, which we'll come back to, I don't want to solve with a cosine and a sine in this equation. So if I can make a substitution to change the sine into cosine or vice versa, get one trig equation in there, then I can try to factor with that one trig equation or get that one trig function or get that one trig function by itself. So we've already seen the concept, right, of using identities to make substitutions. The thing is, now the identities that we're going to substitute in or that we're going to use are double angle identities. So if I substitute in a double angle, which is again what we're going to see happen here, we want to make sure to follow the rules for solving when we have a double angle, particularly with the domain restriction. If we have a double angle, we have to remember to double any domain restriction that is attached to our problem. Now, if we don't have a domain restriction, then we don't have to worry about that piece. But basically, it's going to combine, again, using identities and solving when we have a double angle. And I put those into our notes here so we don't have to go fishing around to too many reference sheets. So let's jump right into number 1. We're going to solve on the interval from 0 to 360 this equation. So hopefully you're recognizing already if we have a cosine squared minus a sine squared, we see that happening in this very first cosine of that double angle. So my goal is to get that, but it doesn't look like that yet. But it's close. If I take this and factor out a 2, that's going to leave me cosine squared x minus sine squared x, and then I'm in perfect shape to make the substitution that I need. So I can swap this out now, right? I just showed you in that box that the cosine squared of x minus the sine squared of x is going to be equal to the cosine of 2x. That's our double angle identity, the first double angle of a cosine, or cosine of a double angle. So when I rewrite this, it's 2 times the cosine of 2x, now equal to negative 1. And now we're basically in the same place we were in our previous topic. Okay, I'm now trying to solve this equation that has a double angle in it. So the first thing I'm going to do is double my domain restriction. So instead of looking from 0 to 360, I'm going to look from 0 to 720 degrees. And I also don't want to make any math errors here. So I'm going to replace this double angle with a theta. So I'm going to let theta equal 2x. Then when I rewrite my equation, it's 2 times the cosine of theta equal to negative 1. And solving for theta, again, this feels familiar, comfortable. So if I divide the 2 over, the cosine of theta has to equal a negative 1/2. And now we go to the unit circle and find all the angles such that the cosine of our angle is going to equal negative 1/2. And remember, when we go to the unit circle, 2 laps around, okay? So go to our unit circle. Let's find angles where the cosine of our angle is equal to negative 1/2. So, and actually we're in degrees. 120 degrees, we have a cosine of negative 1/2. And then again at 240 degrees, we have a cosine of negative 1/2. And I don't have to worry about doing any condensing. We're not looking for infinite solutions. We're just looking for the distinct set of solutions from 0 to 720. So not only am I going to get these two, which are occurring on the first lap of the unit circle, but remember, I can go around a whole 2 pi and then land here a second time. So I'm going to take 220 and add a full 360 to that. And the same thing with this angle. If I add a full lap, full 360, I'm going to get to my next angle. So now I'm going to go here, take the 120 and the 240. So off the first lap of the unit circle, we get the 120 degrees and the 240 degrees. And then I'm adding, instead of a 2 pi, I'm adding 360 to get to my next angle. So 120 and 360 is going to be 480 degrees. And then I'm going to add a full lap, like a 2 pi, 360 to 240. So that's going to get me, what, 600 degrees? Okay, and those would be my 4 solutions for theta. Now, technically, remember, we're not actually solving for theta. I substituted that in. So now I'm going to get rid of theta. I said let theta equal 2x. Well, now I'm going to replace theta back with that 2x. So instead of theta equal all those angles, it's going to be 2x equal to 120, 240, 480, and 600. And so to solve for x, it's just one more step. We're going to get rid of the, sorry, my pen, I don't have any more colors. We're going to get rid of multiply by 2 with divide 2. So everything gets divided by 2, which means our final solutions will be 60 degrees, 120 degrees, 240 degrees, and 300 degrees. And that work feels a lot easier in degrees than it does in radians, so hopefully we appreciate that in that first problem to get us going. Okay, so there it is, plenty of space, also kind of a nice feature. And again, nothing new, just making a substitution with an identity. We've done that before, and then that substitution making a double angle is something we've also done before. So good review, and another opportunity to practice that in number 2. Now, if you're feeling good or like you need the practice, this would be a good place to pause the video and try it out. If you don't want to, totally fine as well. So I'm going to try to substitute in a double angle here. And this looks pretty close. Highlighter. This 4 sine of cosine x is pretty close to 2 sine cosine here. So I want it to look like that. I'm going to do the similar step to what I did in the last one. I'm going to actually factor a 2 out so that I have a 2 sine of x cosine of x left. And then I can see my double angle exactly. So now I can replace that with the sine of my double angle. So that would be my next step here. 2 sine x cosine x is going to get swapped out. It becomes 2 times the sine of 2x, and it's still equal to radical 3. And now I'm solving an equation that has a double angle in it. So before I continue, I have to double my restricted domain. So if I double this instead of 0 to 2 pi, now I'm going to be in radians. I'm going to be going from 0 to 4 pi. And I'm going to put theta in here instead of that 2x. So this is going to be, we're going to let theta equal 2x. And when I rewrite this, I'm looking at 2 times the sine of theta equal to a radical 3. So solving for theta, again, this should feel familiar, not so bad. We're just going to divide the 2 over and look for the sine of our angle theta to be equal to radical 3 over 2. So we're going to go to the unit circle. We're going to find all the angles where the sine of our angle is radical 3 over 2. And remember, over 2 laps, we've got to go around the unit circle 2 times. So let me clean this mess up. All right, where is the sine of our angle going to be a positive radical 3 over 2? So positive radical 3 over 2 for sine, it happens at pi over 3. And it also happens here at 2 pi over 3. So that would be in our first lap. And then I'm going to have to add 2 pi to this one to end here again the second lap. So plus 2 pi to this. And then the same thing here, add 2 pi. So I've got pi over 3 and 2 pi over 3. I'm trying to hold that in my head. So right now, theta is going to be equal to pi over 3 and 2 pi over 3. That's the first lap. Now I want to add 2 pi here. And if you need to, do the work. Like, I can do some of this fraction stuff in my head. If that's not you, that's totally fine. Just write it out. If you have pi over 3 and you're trying to add 2 pi, that's technically 2 pi over 1. You need common denominators. So you'd have to triple the top and the bottom here. Then you have 6 pi plus the 1 pi, so that becomes 7 pi over 3. So that's going to be the next solution. And then I'm going to add 2 pi to this one. So again, if you don't want to do that in your head, if you have 2 pi over 3 and you want to add 2 pi, which again is 2 pi over 1, triple to get your common denominator, and now you have 6 pi plus 2 more here, so that's going to be 8 pi over 3. And now I'm just going to get rid of this because it looks ugly. Alright, so now I have my 4 solutions over the interval from 0 to 4 pi, but remember those are 4 solutions for theta. I need to put x back into this. So I'm going to say 2x is equal to pi over 3, 2 pi over 3, 7 pi over 3, and 8 pi over 3. And then my last step, and I don't have enough colors. Let's try orange. Let's get rid of the multiply by 2 by dividing everything by 2. So x is going to be equal to, back to my blue, so I have first pi over 3. It's being divided by 2, which technically means it can be multiplied by its reciprocal, which is a half. So that 2 is going to end up in the denominator. It's going to make this a pi over 6. And the same for all the rest. But on the next one, you can see you have 2 pi over 3. When you multiply it by a half, the 2's are going to cancel and just leave you a pi over 3. And this will be 7 pi over 6. And this next one is going to be, again, something we can reduce. So I have 8 pi over 3. When I multiply by a half, that's going to become 4 pi over 3. Oops. Eraser turned on. So 4 pi over 3, and those are going to be my 4 solutions over that interval. Okay, so if you need to do the fraction work, do the fraction work. If you can skip some of that, do some of that in your head, then more power to you. Either way. But we did it. All right, so that's one direction where we are actually using an identity to substitute in a double angle and then solving with the double angle in the equation. Now, sometimes we have to go in reverse, and that's what we're going to see in the next two problems. Oh, I'm like, why won't this go? It's because I had my eraser on. Sometimes we want to substitute out a double angle. So, for example, if we're looking at numbers 3 and 4, I have the same trig function in this equation. They're both cosine, but I can't factor or use any of the other strategies because even though they're both cosine, one's the cosine of x and one's the cosine of 2x. It's almost like having two different trig functions because they're different. So, in a case like this, where I can't just solve, I can't just use inverse operations to get this thing by itself, like we were doing in the previous topic and what we did here, right? Once I have my double angle, like I can get this alone by dividing over the 2. So I can't do that in this next problem, or either problem that we're going to see here, because there's function outside of the function. So in a case like this, we want to get rid of the double angle using an identity. So instead of putting a double angle in with an identity, we're going to use an identity to take the double angle out. So I can have just the cosine of x in there instead of cosine of x and cosine of 2x. So I don't know if I'm making any sense. In my head, I am. So we can use a double angle identity, again, to replace a double angle. The same way we can swap it in, we can take it out. And again, this is going to be when we can't solve for the trig function of the double angle just using inverse operations. Once that double angle is out, then we can use known strategies for solving. So if the double angle is out, then we don't have to worry about any domain restrictions or lapping around the unit circle multiple times. We're just going to solve how we normally solve. Now, that sounds simple, but remember, the normal solving entails a lot of different things. So let's see what we're going to encounter here. So I have the cosine of 2x, and I'm going to try to swap this out so that on this side I also have something that's in terms of the cosine of x. So while I have 3 different identities for the cosine of my double angle, I don't want to use this first one because that introduces 2 different trig functions. Excuse me. I don't want to use this one because then again I would have cosine and sine. That's no good. So my choice is going to be in the middle. I'm going to replace my cosine of my double angle with 2 cosine squared of the angle minus 1. So here we're going to swap this out. So I have 2 times my cosine squared x minus 1 equal to my cosine of x. And now we're in a place where, again, this should, oh my gosh, getting all choked up here, I'm sorry. This should feel familiar. Now that we are cosine of x, cosine squared of x, same trig function, just varying degrees, we can try to factor. So I have 2 cosine squared x. I'm going to subtract the cosine x over from the right to the left, and then leave the minus 1, so this is all in order equal to 0. And now I'm going to be looking for factors of negative 2 that make negative 1, like negative 2 and 1. I'm going to divide those by 2 and reduce. So this is going to factor into 1 cosine minus 1, 1 cosine of x minus 1, and then 2 cosine plus 1. 2 cosine of x plus 1. And now that we're in factored form, each of the factors being equal to 0 is going to get me my solutions. So where over the interval from 0 to 2 pi is my cosine of x minus 1 going to equal 0, or my 2 cosine of x plus 1 going to equal 0? So this will be, where is my cosine of x going to equal 1? And I can go to the unit circle for that, and we're just over the interval from 0 to 2 pi. Now what we're solving, no double angle in this thing we're solving, so I don't have to worry about messing with my interval. So from 0 to 2 pi, and I already forgot, what am I trying to do, is this one over here. Where is my cosine equal to 1? I mean, maybe you don't need a unit circle for that, kind of hoping you don't actually. Where's our cosine equal to 1? That's going to happen right here at 0. And technically, we could loop around and say that's 2 pi, but 2 pi not included here. So we're going to say x equals 0. And over here, we want to know where 2 times the cosine of x plus 1 is going to equal 0. So if I subtract the 1 over, and then divide the 2, where is the cosine of x going to be equal to negative 1/2? So back to our unit circle. Where do we have a cosine of negative 1/2? So negative 1/2 for cosine happens here. That's not a good color. Negative 1/2 for cosine happens here at 2 pi over 3. And negative 1/2 for cosine happens here at 4 pi over 3. And again, I don't have to worry about doing any condensing because I'm on this fixed interval. So those are the two distinct solutions I'm looking for in that interval. So 2 pi over 3 and 4 pi over 3. So x is going to equal 2 pi over 3 and 4 pi over 3. And so we have done it. Over the interval from 0 to 2 pi, we end up with 3 solutions. I'm going to go ahead and just nicely put them all together down here. Although you don't have to take this step. You could just box this in, just box that in, and I'd be okay with that. That's generally how I've been doing this anyway. I don't know why I decided to take the step on this one, but let's just mix things up, right? All right. With plenty of space and time to spare, we're going to try this again. Again, if you want the practice, this would be a good spot for you to pause the video. So I'm going to do the same thing in this one I did in the last one. I'm going to get rid of the cosine of my double angle. I can't just solve for this when I have a sine over here. But we've got options for our cosine of our double angle. Since the other side of my equation has a sine, again, I want to use something that's going to get rid of cosine here and make it sine. So if I go to my list of double angles, I don't want to use one that has cosine and sine. I don't want to use the one that just has cosine. I want to use the one that has sine. So this is going to be the winner. I'm going to replace my cosine of my double angle with 1 minus 2 sine squared of my angle. So replacing this becomes 1 minus 2 times the sine squared of x equal to the sine of x. And again, we're in a place that should feel familiar. So I want everything in order equal to 0. In this one, however, when we're factoring, we generally want our first term to be positive. So instead of subtracting the sine x over, I'm actually going to move these terms to the right side. So I'm going to get my 0 on the left. If I add over the 2 sine squared x, it becomes positive. And then the positive sine x that's already sitting here is going to stay. And then I have, this is a positive one here, so it's going to become a negative one on the other side. Alright, so now in order equal to 0, it's just the reverse. And if you don't like seeing the 0 over there, you can put it on the other side. It's totally fine. But basically the same kind of factoring too. What are the factors this time of negative 2 that make positive 1? So 2 and negative 1. Again, divided by 2. This time we're looking at factoring into 1 sine of x plus 1 and 2 sine of x minus 1. So what is going to make the sine of x plus 1 equals 0, and what's going to make twice the sine of x minus 1 equals 0. And so here, if we subtract the 1 over, we're going to try to figure out where the sine of x is equal to negative 1. And this just says solve, so we're going to be looking for all solutions in radians. So where is our sine equal to a negative 1? Only happens here at 3 pi over 2. And as many times as I want to loop around and get there, I'm going to get that same solution. So from this portion of our equation, from this factor, we're going to say 3 pi over 2 plus 2 pi n times. That's going to be part of our solution set. Now on the other, I want to add the 1 over, so 2 times the sine of x is equal to 1. Divide the 2, so sine of x is equal to 1/2. And then I go to the unit circle, find all the angles where my sine is equal to a positive 1/2. So where do I have a sine that is a positive 1/2? So right here at pi over 6, I have a positive 1/2 for sine. And then over here at 5 pi over 6, and I don't know that there's necessarily a nice way to lump those together, so we're going to separately say pi over 6 plus 2 pi n times, and 5 pi over 6 plus 2 pi n times. And then we're going to be done. So x is going to equal, we said pi over 6 plus 2 pi n times, that's what we said, right? Pi over 6, yep. And then 5 pi over 6 plus 2 pi n times. And so we have 3 infinite solution sets there. Now remember, at any point, if you wanted to check your work, you could always plug an angle in and verify that it works. So just as an example, I'm saying pi over 6 is a solution, okay? That means if I plug it into my original equation, I should get a true statement. So maybe in degrees it'd be easier to plug this in. Pi over 6, think about this, is 30 degrees, okay? So the equation says that the cosine of 2x should equal the sine of x. That's what the equation says. If I plug my 30 degrees in there, then what I'm saying is the cosine of 60, twice that 30, should equal the sine at 30. Well, the cosine at 60 is a half, the sine at 30 is a half, and those do in fact equal one another. So if you want to verify your work, you can always plug these things back in, and you can use the calculator to do that as well. Now it's impossible to verify all of the solutions, but if you're not sure that you picked the correct pi over 6, like maybe you know you're supposed to add 2 pi in, but you don't know if this is the right spot, plug it in and see if it works. Alright, so there's options there. And then remember, too, if you wanted to get these correct answers before doing any of the algebraic work, you have the graphing option. If you were to graph this function, or graph these two sides of the equation as two separate functions and find the intersections, these are the intersections that you're going to see over the interval from 0 to 2 pi. So you have so many options for getting the answers. There's not really an excuse to not get the answers, let's say if you were working on a homework assignment, but building the algebraic skills is going to be a necessary beast, okay? But it's helpful when you're working through the algebra to make sure that you have the right answers first, or to verify that you did it correctly after the fact, okay? So you've got options, you've got plenty to work on. If you need some extra help, please reach out. If not, see you guys in class. Until next time, take care.